So at the conclusion of the previous stage of this tutorial, we had already created an any revenue joint object. But when we opened the model view, we did not see any change in the configuration of segment 1. But I said that this was no reason to worry because there were no changes because we hadn't created a simulation or an analysis to run the model through. But before we get to that stage of creating a simulation and actually seeing some kind of motion at our joint, let us take a small step aside and look into two very important concepts in any body, which are those of measures and drivers. And the reason why measures and drivers are important is because they make many advanced functionalities that are unique to any body possible. So to discuss measures and drivers, let us switch out of the any body view and let us switch over to my presentation. Let us just go back to the time when we had our segment 1 freely suspended in three-dimensional space, completely free to move around. And then we are currently at a stage of the tutorial where we have created the revolute joint. And we eventually want to reach a stage where we start seeing some kind of motion between segment 1 and the ground at the revolute joint. Let us first dissect the process of creating this joint a little further. So we had this free floating segment which had all its 6 degrees of freedom at its disposal, which meant that these 6 degrees of freedom sort of consisted of the three Cartesian coordinates, which were the three translational degrees of freedom. You could have also expressed these 3 degrees of freedom in polar coordinates. And you also had three rotational degrees of freedom, which could have been quantified or represented by the three rotation angles of the segment 1 reference frame that you see here in yellow with respect to the global reference frame. Now, when we created the revolute joint, we supplied two reference frames to the any revolute joint object, and these were the ground reference frame and a reference frame that was associated with this ground connection node on segment 1. And the purpose of creating the joint was to firstly to make these 2 points coincident, which means that you wanted the vector r to be of 0 magnitude. So which means that all three components of this vector had to be 0. So this would have arrested the three translational degrees of freedom. And additionally, if we were to look at the three rotation angles of segment 1 with respect to the global frame, we had the revolute joint which only permits rotation in a single plane. And in this case, this plane was the XY plane. And for this reason, the two of the three rotation angles, which were just theta x and theta y, were set to 0 when the revolute joint was created. So this also arrested 2 degrees of freedom. So in total, 5 degrees of freedom, that is 3 plus 2, were arrested by the creation of the revolute joint, which left our system with only one remaining degree of freedom. Now, if we were to just to reiterate these two steps in creating a revolute joint again, we had step 1, which was to measure the vector r and the three rotational Euler angles, or any three rotational angles, and step 2, which involved constraining all three components of our vector r and two of the three rotation angles to 0. So totally, this arrested 5 degrees of freedom. Now, this is exactly how, oops. Now, this is exactly how anybody goes about creating a joint as well. That is using these two steps. So step 1 is enforced by a set of tools that are called kinematic measures, while step 2 is enforced by a set of tools known as drivers. And so which means that each driver is associated with a certain kinematic measure, and the driver then drives or constrains the value of that measures to a certain desired number, which in this case happened to be 0. So when we created the any revolute joint object, this automatically created the measures and drivers required for constraining these 5 degrees of freedom. So this was just automatically done, but an alternative would have been to do this manually. So to create the same joint, you could have used two sets of measures. So these could have been using the classes anykin linear, which is used to measure the translation between two reference points in your model. And you could have used any kin linear to measure r, the vector r, and you could have used any kin rotational, which is the rotational equivalent of any kin linear, to measure the three rotation angles. Now, I will leave it to you to read up more on these classes from the AnyScript reference manual because they're fairly straightforward. And once you had created these measures, you could have actually created drivers to drive the values of these measures to zero. So for driving, you could have used this class anykin EQ, or as an alternative, you could have used anykin EQ simple driver. And both of these are sort of, again, fairly simple classes, which I think you can read up on more in the AnyScript reference manual by yourself and understand them quite easily. So if we had chosen to create the joint using any W joint, or alternatively using the manual technique of specifying the measures and drivers ourselves, these two techniques would have been exactly equivalent. So all that this class on the left is doing is just making life a lot simpler for you. So we've discussed the creation of the W joint, but now let us look at how we would add motion to our model. Now we must remember that there is still one degree of freedom of the system that is free and can be manipulated in some way. And so in principle, we can actually assign a driver to this one degree of freedom. Of course, if we can measure that one degree of freedom using a kinematic measure in the first place. And it must also be remembered that drivers are capable of enforcing time-varying constraints and not just fixed constraints, as we saw in the case of the NEW joint, where they were driving the values of all the measures to a fixed value of zero. So you can use drivers to impose a time-varying trajectory on the value of a kinematic measure. And a potential candidate for such a driver is the anykin EQ simple driver that we also saw in the previous slide. And this is a driver that can be used to constrain a measure to either a constant position value, or to make it move at a constant velocity or a constant acceleration. So we've spoken about the driver and we've spoken about its capabilities of producing motion. But in the case of our one segment model, what is the measure that needs to be driven? Now, we mentioned that there is one degree of freedom that can be driven. And so a potential candidate for this measure is the joint angle of the revolute joint, because this exactly constitutes one degree of freedom. But before we go into talking about how we can create this measure for the revolute joint angle in anybody, let us go back to the time when we were discussing classes in the tutorial. So this was a few sections ago, and we spoke of a class hierarchy, which meant that all classes in anybody can be organized in this giant family tree, where you have child classes that inherit certain attributes of the parent, in addition to having certain special attributes of their own. Now, we also discussed that any folder was the class that was at the very top of this family tree, which means that all other classes are descendants of the any folder class. Now, one of the descendants of any folder is anykin measure. And it must be remembered that this is a descendant and not a direct child of any folder. So which means that this dotted line that you see over here is actually an entire subsection of the family tree between anykin measure and any folder. And anykin measure is actually the base class for all kinematic measures in any body. Now, the classes that you use to create joints in any body are actually descendants of the anykin measure class. And these joint classes, of course, include any revolute joint that we use to create our joint between segment 1 and the ground. So since any revolute joint has descended from any kin measure, any revolute joint is also a kinematic measure. And so you can use an any revolute joint object as a surrogate for the joint angle kinematic measure. Now, this was a piece of information that I have given you, but let's say you are faced with a completely new class that you've never encountered before. How exactly would you go about finding out its parents, or the classes that it's descended from? So for this, let us switch back to anybody, where I will now use the help drop-down menu and go to the AnyScript reference manual. Now, in the reference manual, you have the search functionality, which is over here on the left. And over here, I'm going to search for any revolute joint and click on list topics. So you can see that the entry for the class is the first in the list. Now, below the name of the class, you can see this particular statement over here, which says base class any cylindrical joint. Oops, sorry, my pen suddenly got really thick. Yeah, you see that the base class for this joint is any cylindrical joint, which means that any cylindrical joint is the immediate parent of any revolute joint. Now this text is actually clickable, so which means I can click on any cylindrical joint, and this will take me to the corresponding article. And over here, there is a second base class that has been defined, which is again the immediate parent of any cylindrical joint, and this is any STD joint. So I can keep clicking on these base classes, and sort of what I'm doing is actually navigating upwards in the family tree of classes until I get to any kin measure. And you can read the description over here and understand that just as we discussed, any kin measure is the base class for all kinematic measures. So you could repeat this whenever you're faced with a new class whose ancestry you want to trace. So going back to the presentation, we've now discussed the fact that any revolute joint is a surrogate for your joint angle as a measure. So you could use this as a measure and any kin EQ simple driver to, in this particular video that you're seeing, I've actually used any kin equal simple driver in the constant velocity mode, and that is why you saw the segment rotating at a constant angular speed. But then I could ask the question: are these choices of measures unique? Uh, but then I could ask myself the question: are these choices of a measure unique? The answer is no. I could have actually used any 1 degree of freedom measure as an alternative to using the joint angle. So for example, I could have used this particular class, which is called anykin COM, which is used to measure the three-dimensional coordinates of the center of mass in Cartesian space. And I could have just isolated one of the three coordinates which correspond to the height of the center of mass. And I could have then used a driver, such as this one, which is called any kin EQ Fourier driver. And this is the class that is used to drive a certain measure along a trajectory that is given by a Fourier function. So I can use this to drive the center of mass along a sinusoidal trajectory. And this would have given me a completely different motion from the previous case. So you can actually choose your measures and drivers based on based on convenience. So you don't, in this particular case, it was more convenient to use my center of mass. But then in a case where it is more convenient to use joint angle, I could have used any revolute joint. The thing that is most important is that irrespective of what measure you choose, the total number of degrees of freedom represented by those measures should be the same. In this case, this had to be 1 degree of freedom because this was the only free numbers of degrees of freedom that we had in our system. For some final observations, we had our one segment model where it must be observed or noted that the number of drivers were actually equal to the number of free degrees of freedom that we originally started with. So we started off with a 6 degree of freedom segment, and then we arrested 5 of these degrees of freedom by adding the revolute joint. And then we arrested 1 more degree of freedom by adding the motion driver. So it would be tempting to generalize this and say that for any complex model in any body, especially human models, which have the default human model in any body has many degrees of freedom. So it would be tempted to say that the number of drivers must equal the number of degrees of freedom. But this statement is only partially true because instead of the equality, it is actually a greater than or equal to sign. So which means that the number of drivers can actually exceed the degrees of freedom. I won't go into the reasons for this I won't go into it in a lot of depth over here, but to explain it briefly, this is because drivers can actually be classified into 2 categories: hard drivers and soft drivers. Now, in a hard driver, the constraints that it enforces always need to be exactly met by the simulation, and the simulation will fail if it does not succeed in doing so. But the soft driver goes a little easier in the simulation, and it only asks it to satisfy those constraints to the best extent possible. So if I had a model which had, say, 10 degrees of freedom, the only thing that's important is that the number of hard drivers not exceed the total number of degrees of freedom. So I can have my hard drivers ranging from 0 to 10. So let's say I have 8 hard drivers. Beyond that, I can add any number of soft drivers that I want. So I could add, it's theoretically infinite, but I could say I could even add 20 soft drivers and still have a feasible simulation. But on the other hand, if I were to have 10 degrees of freedom over here and 12 hard drivers, this would not be possible because the simulation will try to satisfy all these 12 constraints exactly, and what you actually have is an over-constrained system. So this should conclude our discussion on measures and drivers. And in the next section of the tutorial, we will go back to Anybody and look into how we can implement these drivers in practice